Good morning, everyone. Welcome to the 10th practical of fiber optic communication, that is to plot the characteristics for a LED. Now we know that for an LED, it gives us a direct relationship between the current and the optical power output. So the relation between the optical power output and the forward bias current is given by this relation where eta represents the efficiency, I the forward current, H is the Boltzmann constant, E is the charge of an electron, and F is the frequency of the input signal. So using this relationship, we have to make a plot between output power and the input forward bias current. So the simple relationship, we have to plot it in a lab view. So we will open our lab. So if we look at our equation, what we need at an input is an efficiency, the current, and the frequency, which we will represent in terms of wavelength. F is C by lambda. So what we will do is first select our input terminals, forward current in milliamperes. Then for efficiency, we'll select the knob. Okay. And the next thing that we need is the wavelength in micrometers. So the maximum wavelength is 1.7 micrometers and the minimum is 0.8. Now to see the output, that's the optical power, we need again a gauge in milliwatts, and then we will use a extended XY graph to see a relationship between optical power versus the input forward current. So this much we need. We can now go to our block diagram window and make the required connections. Now to start, we will take our formula board. Eta, wavelength, forward current, that is I. So we have all the inputs. So we can look at the formula. It is eta into I into Boltzmann's constant into C, that is 3 into 10 to power of 8 divided by wavelength, which is in micrometers. So we'll multiply it with 10 to power of -6 into, in the denominator we have E, that is 1.6 into 10 to power of -19. Okay. Now the current is in milliamperes and we haven't multiplied it with the factor 10 to power of -3 because we want the output power in milliwatts. So directly it will give us the output power in milliwatts. So now we will make our connections. The output is on the gauge, as well as we'll connect the output to the, and the input is the forward current. Now we'll set this to false by creating a constant and converting true to false. So our circuit is complete. We can just go to our front panel and adjust our values. Let's keep our forward current at 4, efficiency at 0.5 and wavelength at 1.5. We can have our digital displays for all the values for the ease of noting down their values. Okay, now we can just continuously run it. So what we see is we are not able to see the output. So what we will do is, for getting the output, we will just introduce a structure, say for do loop. And since we want our forward current to vary till 10, so I'll just create a counter. And instead of forward current, I will connect this counter. So this is actually, that will help us to vary our x-axis as per the counter and get our output. Let's see the output we are getting or not. You can see a straight line. You can just change the color as well as the thickness for better visibility. And now we can continuously run it and see what is the change in the value with the change in the wavelength. You can clearly see on the gauge as the wavelength is changing, the optical power energies are changing. And this is what you have to do is, for the corresponding current, what is an output that is there, you can and once you have the cursor, just right click on it. So create cursor, you can have a single point or a multi-point. So I just take a single point and then you can just make your X values. You can just vary the X values and corresponding Y values will come. And this is how you can note down your values and make this plot on your graph paper. You can even change this on the axis labels. So this is what you have to do to see the response of an LED to the input forward current. Okay, thank you.